Anyway. Alright, so we're talking about work today. Let's get going, guys. Let's get started. Let's get going. We've had in all my classes so far, I have two correct solutions for the problem of the week. So we got a couple people. Yeah, that was not the solution. The solution was not that the problem of the week doesn't exist. So we've determined that the problem of the week does exist. So we're part way to getting a solution. Now several people found it and solved it. All right. So we are talking about work today. The next couple of lessons, we're doing applications of integrations and also kind of application problems in general. We're applying calculus to kind of real world situations. A lot of them are kind of contrived, but we're working towards it. Work has to do with lifting or pulling, springs, rocket propulsion, pumping liquids into tanks, and we're basically talking about how much energy is needed to do these things. And we'll start out really quickly by talking about a constant force. Things are less interesting when forces are constant. So for a constant force, and by force we're talking about some kind of push or pull, something like that. For a constant force, so we move an object through some distance. For a constant force, I'm going to say F. Object moved through some distance D. The work is just the force times the distance. Work, W, is the force times the distance. So if we're lifting some 50-pound object and we lift it 4 feet above the ground, we're doing 50 pounds times 4 feet, or 200 foot-pounds of work. Near the surface of the Earth, we assume that the force is constant. And a couple of important points about units. Pounds is a unit of force. So in the imperial system, rather than using units of mass, we use units of force. In the metric system, and then so let me go back. Pounds are a unit of force, and work is usually in foot-pounds. Foot-pounds, mile-pound, inch-pounds, something. That's usually the unit that we'll use. In the metric system, the units of work are going to be usually Newton meters, which is a joule, or a dyne centimeter, which is an erg. Yeah, erg. And 1 joule equals 10 to the 7th ergs. So just a little bit about units. I was talking with a friend of mine who's a teacher up in Fort Collins, and her daughter was learning unit conversions, what do they call it, dimensional analysis, is what they were calling it. And I told her how I hated having to deal with units. It's so much nicer when you just deal with nice equations. You don't have to think about the units. But what we're interested in, not that that matters at all. So what we're interested in, we're not interested in constant forces. Because we're studying calculus, we want things to vary. So we want to find the work done if we have a variable force. So let's talk about a variable force. That's when things start getting interesting. So if we have, so let's say we have a force that varies as we're moving along the x-axis. So we have f is some function of x. So what we're going to do is divide the interval where we're moving the object along. So we're moving this object from point A to point B. So we'll divide this interval into small subintervals. Should sound familiar by now. So we just chop it up, divide it into intervals, and so in the ith subinterval, in just one of these subintervals, our work is the work done in that small interval. We'll call it delta W sub I in that tiny little interval, is the force at that point, and I'll call the point C. Force at point C sub I times delta x sub I, so the length of a little interval. And we're saying that f at c sub I equals force in the interval. And then we're just going to sum this work over the entire interval. So the total work is the sum of these. And I'm going to say approximately because we're dividing this up, chopping it up. Sum I equals 1 to n of delta W sub I, which we said was going to be our sum of our force at this point times delta x sub I. And as we chop this interval up into smaller and smaller and smaller pieces, this is essentially a Riemann sum, and we get a nice integral. We have the work is the integral from A to B of some of our variable force dx. So the work done moving an object from point A to point B by a variable force is given by this integral. So there are going to be several types of problems that involve a variable force. We're going to talk about lifting problems. We're going to talk about pumping problems. Those are the two primary kinds: lifting problems and pumping problems. So when we're lifting something with a mass, as we lift more of it up, we have to apply more force to continue lifting. And if we're pumping a liquid, so say we're emptying a tank, we're pumping the liquid at the top of the tank moves a smaller distance than the liquid at the bottom of the tank. So as our distance varies, we have to apply a different amount of force to pump that liquid. And then things also get interesting if our tank that we're pumping into or out of, where the volume of a small piece changes as we move up or down or side to side. in the tank. So what I want to do is just do a couple of examples using a lifting, with a lifting problem and with a pumping problem to show you the kinds of problems that you'll see in your homework, how we're going to apply this idea of work, and how we set these problems up. Usually with these kinds of application problems, the setup is more difficult than the actual calculus involved. So let's look at those. So we have a climber, and he has a 50-meter rope. And it's coiled up on the ground. And this climber wants to pull it up so that it's completely extended. And we're going to say that the rope weighs, or the mass of the rope, is 0.624 newtons per meter. So we know how much the rope weighs per meter. So how much work is this climber going to do? So for these kinds of problems, I always recommend draw a little picture. We're going to draw a little picture. Put a little steps over here. We want to find the force, and I call it the increment, so a little piece of force. And we want to find the distance that each section moves. And then we integrate. So we're going to integrate over the distance that we move. So what we have, let me draw a picture here. Here's my rope coiled up on the ground. And what we're doing is we're going to take it from here so that it is finally fully extended. And this length would be 50 meters. So we can define a coordinate system and decide how we want to divide this up. I always try to set 0 at a very convenient place. So I'm going to put 0 down here at the bottom of the rope. I'm going to say this is y. So that's my y-axis. So I want to find the force increment. Well, the force increment is the weight of a small piece of rope. So the force, and I'm sorry, I misspoke here. This isn't the mass of the rope. Newton isn't a measure of mass. Newton is a measure of weight. So this is the weight of the rope. Mass would be kilograms or something like that. So we have the weight of the rope. Well, the force that it takes to haul up a tiny little section of rope is the weight of that section of rope. So I'm going to look at a tiny little piece of rope. This little piece, and the thickness of that little piece I'm going to call dy. That's my tiny little piece of rope. And that tiny little piece of rope I've lifted a distance of y. So the amount of force that it takes to lift this little piece of rope or the work done in lifting that small piece of rope is its weight times the distance that is lifted. I want to say work. Work for each small section is the weight times the distance that is lifted. So what's the weight of this tiny little piece of rope? We know it's 0.624 newtons per meter, and dy is measured in meters. So the weight is going to be 0.624 dy. Tiny little piece of rope, and the weight of that tiny little piece of rope is going to be the weight per meter times the length of that little section. The length of that little section is dy. Weight per meter times the length of that little section. So the force to lift that tiny little piece up by or the work to lift that tiny little piece up by y meters is 0.624 y dy. I've lifted that little piece up by y units. And y here varies from 0. I don't lift this piece that's touching the ground at all, and I lift this tiny little piece that's at the top the entire 50 meters. So the total work is going to be the integral from 0 to 50. Piece down here I don't lift at all, and the piece that's up here I lift the entire 50 meters of the work done to lift one small piece, and I'm adding all of those up. Nice easy integral. This gives me 0.624 y squared over 2. Evaluated from 0 to 50, and I should get 780 Newton meters. So for lifting problems, the procedure that you want to follow is, from your picture, you want to divide whatever you're lifting into tiny little pieces. Find the weight of that tiny little piece. The weight is going to be the force that it takes to lift it up. Set up a coordinate system so you know how far each little piece is lifted, and then you integrate over the distance that they're lifted. You have questions? Now let me add something to this problem. What if once the rope was extended, so as I pick the rope up, the very first piece, the rope, it doesn't take much work to lift the first piece up, but then as I'm lifting it up, I'm extending it more so that I'm lifting more and more and more of it. What if after I extended it fully to 50 meters, then I wanted to lift it another 10 meters? How would I find the work then? How does that change the problem? So I'm lifting it, I'm extending it, it's coiled on the ground, I extend it up, now it's fully extended. Now I'm going to lift the entire rope up an additional 10 meters. How would I account for that additional piece of information? The force times 10 meters, and how would I find the force? What's the weight that I'm lifting? Someone said it. The entire rope. Once I extend it, once I have it fully extended, then I'm lifting the entire rope up. So then I would just have the weight of the entire rope times the 10 meters that I lifted. So then that first 50 meters, the rope would be being lifted by a variable force because I move each piece through a variable distance. But then once it's extended, I'm lifting the entire rope 10 meters, so I'd have the entire weight of the rope that I'm lifting 10 meters. So some of the problems add that little piece on to see if you're kind of paying attention to what's going on. All right. The second kind of problem that we like to do with work is a pumping problem. So for pumping problems, I'm going to suggest that you draw a picture with a coordinate system. Often the problem is more difficult or more easy depending on how you set up your coordinate system. With pumping problems, we're usually working with liquid. So the second part is we want to find the weight, and I'm going to call that delta F. The weight is a force of a thin slab of the liquid. Find the work. To lift that particular slab. So the work is going to be the weight of that slab times the distance that it's moved. And then we integrate over the depth of the liquid. Or if we're lifting further, we integrate over the distance that the liquid is lifted. So very similar to lifting problems, pumping problems are essentially lifting problems, but we're lifting liquid. So that makes it a little different. So let's do an example of a pumping problem. So we want to pump the water from a full upright cylinder tank. The radius is 5 meters, and the height is 10 meters. So we're pumping this water pumping it from a full upright cylindrical tank, and we want to pump it to a level 4 meters above the tank. We want to know how much work. And we also know that water weighs 9,800 newtons per cubic meter. So I'm going to draw a picture here. So here's my tank. This is 10 meters high. My radius is 5 meters. And we're pumping the water up to a level 4 meters above the tank. So I'm going to set my coordinate system with y going up. So I'm going to set this as my y-axis. And we're going to divide this liquid into little slabs. So here's my little slab of liquid sitting there in a tank. I'm going to call the little thickness delta y or dy, either one. This little slab is at a height y above the ground. And what's the distance that I'm going to pump this little piece? If I'm going to pump it up to here, what's the distance that I'm pumping that little slab of liquid?
14 minus y.
14 minus y. And I always double check myself if I'm not 100% certain. I say, okay, if I'm down here at the bottom, how far am I pumping this little slab at the bottom of the tank? Well, y equals 0, so I'm pumping that 14 meters. At the top of the tank, y equals 10, I'm pumping that little slab 14 minus 10, or 4 meters. Okay, so that tells me I've set things up properly. So how am I going to find the weight of this little slab of liquid? What do I need to do? We know it weighs 9,800 newtons per cubic meter. So what do I need to find? What quantity do I need to find of that little slab of liquid? The volume. I need to find the volume, because I'm given the weight of the water per unit volume. So the volume, I'm going to call it delta V or dV. The volume of that little slab is what? Pi r squared dy, and the radius is 5. So 25 pi dy, and that would be our units in cubic meters. So the dF the weight dF of our slab is this volume times this density. 9,800 times 25 pi dy. That would be the weight. And how far are we pumping each slab, did we decide? Each little piece? How many meters? 14 minus y units. So the work done for that little slab, I'll say dW of the slab, is this quantity multiplied out is 245,000 pi times 14 minus y dy. And then I'm going to integrate over the distance that I'm pumping the water. So my integral is going to go from, what's going to be my limits of integration here? going to be 0 to 14. So let's think back. If y equals 0 here, how far am I pumping this little slab? 14 meters. If y equals 10, how far am I pumping this little slab? 14 minus y, yes. But I want to know my limits of integration. So if I'm up here at y equals 10, I'm pumping that thin little slab 4 meters. So y is going to vary from 0 to 10. This 14 minus y takes care of this extra distance of 4 meters. So we can double check yourself by making sure that you're pumping each piece, each little slab, the right distance. If y equals 0, I'm pumping this little slab the entire 14 meters. Y equals 10, I'm pumping this little slab 14 minus 10, or 4 meters. So I get everything going up as far as I want it. So 0 to 10 of this quantity. Nice, easy integral to evaluate, and I get that this comes out to be approximately 69272118 joules. Now, sometimes in these pumping problems, they like to set up the container so the radius varies as the height changes. So if that's the case, then you need to express the radius of your little slab of liquid in terms of y. So you're going to have to use the geometry, the shape of the tank, to express the radius in terms of y. So rather than a nice, here our radius stayed constant at 25. If this were a cone shape or a spherical shape, the radius would change as we pumped the liquid up. So we would have to have some kind of expression in terms of y for the radius. And part of the challenge of some of these problems is finding that relationship. So you just use the geometry of the shape. All right, so class ends in just over 5 minutes. Would it be helpful if I posted online working through a couple more of these examples? Okay. I will do. I'll do another example of a spherical tank. So the radius varies as we pump the liquid out of the spherical tank, and I'll do another set up another lifting problem. So I'll post that as section 7.5 supplement or work supplement. Something like that. So working through a couple more examples. All right. We're on page 483. All right, there you go.